All right, the focus of this module is gases and their properties. Um, the sections are modeling a state of matter, gases and gas pressure, gas laws, the experimental basis, the ideal gas laws and chemical reactions. We'll do a little stoichiometry there. Gas mixtures and partial pressures, the kinetic molecular theory of gases, diffusion and effusion. So this is how gases spread or go through walls, so to speak. And the non-ideal behavior of gases in contrast to the ideal gas law. So let's go ahead and get started here with modeling a state of matter, gases and gas pressure. All right, so the goal here is to describe how pressure measurements are made and the units of pressure. And when we say how they are made, not necessarily physically how they are made, but more the units of pressure. We will talk a little bit about how they are made, especially in atmospheres, that's one of the units, and millimeters of mercury, that's another unit. So let's look at gas pressure. The pressure of a gas is due to gaseous molecules colliding with objects, like the side of a container. So the pressure inside of a container is due to gaseous molecules hitting the inside of the container. And the pressure from the gas is going to be proportional to the velocity squared of the molecules that are gaseous. It's also going to be proportional to the mass of the molecules. And so this is kind of interesting. If you have a large molecule moving slowly compared to a small molecule moving fast, these guys can have the same pressure. You should also note that the kinetic energy is equal to mv squared over 2. So we can see that the kinetic energy increases with the square of the velocity, just like the pressure. And the kinetic energy increases with the mass of the velocity, directly proportional. Let's look at the gas units. The gas units we use in chemistry are millimeters of mercury, which is abbreviated mm, uppercase Hg, or atmospheres, which is abbreviated ATM. Sometimes we use torr, and you should know these values here. 760 torr is exactly 760 millimeters of mercury, so a torr is just another way of saying millimeter of mercury. And 760 millimeters of mercury is equal to 1 atmosphere, and that's defined. So that means that there's infinite number of Zig figs here, an infinite number of Zig figs here, and an infinite number of significant figures here. So that's defined. Do not worry about pounds per square inch or pascals or bars, but roughly speaking, about 15 pounds per square inch is equal to 1 atmosphere. So let's look at the origins of 760 millimeters of mercury. So what I have here is a straw. You can see it's open on this end and it's open on this end. And it's inside of a container with liquid in it. And there's 1 atmosphere of pressure pushing down on the liquid. And through the opening in the straw, there's 1 atmosphere of pressure pushing down on the liquid inside the straw. So when we look at the level inside the straw versus the level of liquid outside the straw, they're going to be at the same level because the pressure pushing down is the same on either end of the straw, so to speak. So this pressure here is actually pushing the water up the straw with 1 atmosphere of pressure. And this pressure out here is pushing the level of water down the straw with 1 atmosphere of pressure. So when those pressures are the same, the level inside the straw will be the same. So the inside pressure and the outside pressure are the same. Now imagine, if you will, you blow into the straw, you're essentially increasing the pressure on the inside of the straw. And what happens to the level of the liquid? Well, it lowers. And of course, you can get it to lower to the point where you're actually blowing bubbles out of the end of the straw. But let's say that you don't do that. So let's say that you can steady this like this. You blow into the straw. That means that the pressure inside the straw is greater than the pressure outside the straw. So that's what happens essentially. And there's not enough pressure basically pushing up the liquid to counteract this 1 atmosphere, or this greater than 1 atmosphere pushing down. The opposite happens if you draw on a straw, like you want to, drink some liquid through the straw. When you draw on the straw, the pressure here on the inside of the straw is less than the pressure on the outside of the straw. And so what will happen is the liquid is forced up the straw by the pressure of the atmosphere outside of the straw. So this is a very interesting dilemma if you happen to be a Moonchen. A Moonchen is a creature who lives on the moon. The moon has no atmosphere, so if you have a nice tasty beverage and you have a straw in that beverage and you try to draw liquid through that straw, it will not work because there's no atmosphere on the moon to push the liquid up the straw. So Moonchens have a very clever way of dealing with this issue of not being able to use open cups. What they do is they use pouches and they squeeze the pouch and it squeezes or adds that pressure you need to push the liquid up the straw. So if you ever watch a movie or TV program where you see some Moonchen using a cup with a straw and saying, oh, that was a tasty beverage, you know it's not real. Okay. So we still haven't gotten to the origin of 760 millimeters of mercury, but we're getting there. So here we see the same thing again, 1 atmosphere outside the straw, 1 atmosphere inside the straw. So the level is the same inside and out. Now imagine that the liquid in here were H2O. And now imagine that this straw was extended so it's about 40 feet long or so, or 34 feet long. So here I have this little cutaway because this is a really, really long straw. You can see it's still open on this end, and I still have 1 atmosphere pressure pushing the liquid up the straw. But on this end, we have a closed end. And inside of this little spot here, there's no atmosphere, no gas. It's sealed. Now, normally when you have a space where there's no gas in it, no pressure, we call that a vacuum. So we essentially have a vacuum here. So very little pressure. So how far would this 1 atmosphere of pressure push the liquid up the straw? And the answer is 33.7 feet or 10.3 meters. So we could actually measure the pressure of the atmosphere if we had a 34-foot long straw with no gas in the top of it and it were dipped in water. If the level of the straw were at 33.7 feet, we know there's 1 atmosphere of pressure. If it were greater than 33.7, we know that there was more than 1 atmosphere of pressure. And likewise, if there was less than 33.7 feet, we know there's less than 1 atmosphere of pressure. So the disadvantages of using water to measure pressure, and by the way, this is something called a barometer. The disadvantage, of course, is that to use something like this, you're going to have to climb upstairs 30 feet to be able to read the barometer, or you have to dig a hole in the ground that's 30 feet deep so the barometer sticks out of it inside of a cup of water, and then you can read at it just by standing at ground level. So what's the solution to having such a tall barometer? And the answer is put mercury in it. So you can see I've taken the straw, which is sealed on the end with no gas in it, and it's open on this end, and I put it in mercury instead of water. Now, mercury is 13.5 times more dense than water. And really, if these straws are the same size, the atmospheric pressure will hold up the same mass of liquid. So the mass of liquid in the mercury thermometer or barometer compared to the mass of liquid in the water barometer would be the same. But because mercury is much, much more dense, the height of mercury in the barometer would be 13.5 times lower or shorter. So if there is exactly 1 atmosphere of pressure pushing down on the mercury, how far up will the mercury be pushed above the level of mercury on the outside? And the answer is exactly 760 millimeters of mercury. To give you an idea of what that is, 760 millimeters of mercury, it's about 3/4 of a meter. And you may recall that a meter is about 3 feet. So we're talking about a pretty good distance for mercury. But it's a heck of a lot better than having a water barometer. So that's the origin of the 760 millimeters of mercury being 1 atmosphere. So let's take a look at some pressure unit conversions. We're going to do this atmosphere thing. We're not going to do the bars. We're not going to do the kilopascals. Don't worry about that. So we want to convert a pressure of 635 millimeters of mercury to atmospheres. And we need to remember that 1 atmosphere is exactly 760 millimeters of mercury. So that's our equality. We're going to start off with 635 millimeters of mercury. And we're going to multiply by 1 atmosphere over 760. You can see that the answer is going to come back to be atmospheres. And it'll be a little bit less than 1 atmosphere. So let's see what the answer is. And how many significant figures are we allowed? Remember, this is exact. So there's infinite zig figs here and infinite zig figs here, and we have 3 here. So 3 zig figs is what we should have. And we get, I'm going to change this to flow. And we get 0.836 atmospheres. And that's your answer. Okay, that was really easy. Now I'm going to show you something else here with another problem. This is a manometer, not a barometer. So with a barometer, it's kind of like a tube inside of something. With a manometer, it's a U-shaped container. So here on this side of the U-shaped container, we've got this open to atmospheric pressure. So we're going to pretend there's exactly 1 atmosphere of pressure pushing down, not exactly, but 1.00 atmospheres of pressure pushing down, which is 760 millimeters of mercury of pressure pushing down on the mercury inside of the container. So here we have the container, which is closed, and it's a gas, and it's pushing down on the other side. Okay, so the difference in levels is 35 millimeters. So is the pressure inside the container greater than or less than 760 millimeters of mercury? Well, since this level is lower than this level, the pressure over here must be greater. So the pressure in the container must be greater than 760 millimeters of mercury. Okay, so what is the pressure in the container? Well, to do that, we simply take the 760 and add the 35, and we get the pressure inside the container is going to be the sum of the two. So we get what? 795 millimeters of mercury. So that's the pressure inside the container. So just as a thought experiment, what would happen if we released some of the pressure from the container? We know there's 795 millimeters of mercury in there. What would happen if we released 95 millimeters of mercury worth of pressure? What would happen to the levels here? Okay, so let's see. We've released 95 millimeters of mercury, which would put the container at 700 millimeters of mercury. Well, this would shift so that this side was higher than this side, and the difference would be about, well, if this were 700 and this was still 760, the difference would be about 60 millimeters of mercury. Okay, so that is your first section for this module. please watch the next video.